Hi guys, here we are. We are starting Unit 16. This will be our last full unit. We may or may not do another partial unit. We'll just kind of see what happens there. But this one is acids and bases. Lots of, today especially, will be review. We studied this when you guys were in physical science. So this should sound familiar. Hopefully it does. So first off, just some properties. Acids. Acids as a chemical or anything that give up, or we'll talk about in a minute, will donate a hydrogen, or sometimes they're called protons, when dissolved in water. So when you put them into water, there will be an H or a hydrogen ion formed. Also chemically, they react with litmus paper to turn red. I have red in quotes on this page because if you remember what our litmus paper looks like, it's actually more of a kind of a pink color. So the red is a little bit misleading. Another reaction they have with a chemical is phenolphthalein, which is that big long word there. Phenolphthalein is an indicator, which we'll talk about in a minute. And it's kind of not a big deal because with acids, phenolphthalein don't do anything. Phenolphthalein is a clear liquid to start with, and in an acid, it's still a clear liquid. All right, taste-wise, acids have a sour taste, so think of things like lemons or oranges, those kinds of things. That was one of the first ways that they were actually identified, was by taste. We do not do that anymore for obvious health reasons, so that was kind of an old way of classifying acids. pH. An acid will have a pH of less than 7 on the scale, and again, that's something we will cover kind of down the road a little bit as far as what pH is. Acids are things that will react with metals to form hydrogen gas. It's a single placement reaction. The hydrogen gas, if you remember, I know this has been a long time, but the lab we did, way before Christmas, when you guys, it made the little funny kind of popping noise when you put the match down into the test tube. That was because hydrogen gas had been formed. It was a reaction with magnesium metal. Okay, and then the last one, they conduct electricity. This is because acids dissociate in solution, and so they form ions. The ions will carry electricity. Now, real quick, just something to be aware of. The words that I have in green up there are indicators, and an indicator is any substance that is one color in an acid and then another color in a basic solution. And so it makes it very easy to determine, are you dealing with an acid or base? Because acids and bases typically are clear liquids. So by appearance, you can't really tell, but if you have an indicator, then you can do a real quick little test. Litmus paper, of course, is the easiest. You don't have to do anything besides stick a little piece of paper down into the liquid. Litmus paper is actually derived from a certain type of algae and lichen, and then it changes colors. There are lots of plants that do that. We would have done a lab where I had cabbage juice and carrot peelings, like the liquid from boiling those, apple peels, all those kinds of things, and they are natural indicators, and so they would have turned different colors. Some flowers are natural indicators. They're different color depending on if the soil is acidic or basic, and so naturally there are lots of ways to tell the difference between acids and bases. Okay, so now real quick, some properties of bases. Some of these are going to be the same, or some of them are just going to be the opposite of an acid. So first things first, the dissolving in water, and a base will give up a hydroxide ion, will give up OH when put into water. And so again, it's just the formation of an ion. Litmus paper reacts with bases to turn blue, and it is a pretty true blue color, maybe kind of a lighter blue, but it is pretty well identified as blue. Then the phenolphthalein, here's the one that we really see the change in, and it turns a really kind of a vivid pink color. We have used phenolphthalein before, and so if you think back, I know it's been a while, to some of these labs, if we ever had a liquid that turned a real like magenta color, that was phenolphthalein. Bases, taste-wise, are bitter. So think about like putting soap in your mouth. that is a base. Soap is a base, and so that's the bitterness that you taste. Soaps also, or excuse me, bases also, just like soaps, have a slippery feel, and so they tend to react with the oils in your skin and form kind of this little slick layer. So if you get them on your skin, it's pretty noticeable. pH, they are greater than 7. And then again, because of the ion formation, they do conduct electricity. Okay, so now some uses of these acids and bases. There's more than this. These are just kind of the highlights there. So first off, hydrochloric acid. We actually use this quite often in the labs. It's kind of the common kind of lab acid that gets used as far as some of the high school labs that we do. It is also known as muriatic acid. Lots of times that's what they add to swimming pools. That's where the chlorine in swimming pools comes from. It is also the acid that is in your stomach. And that is a very strong acid, can break down most things. It is, we'll talk about again how strong and weak is determined, but one of the stronger acids. Phosphoric acid, the H3PO4 that's next on the list. If you look on the list of ingredients in like Coke or Dr. Pepper, Pepsi, any of the darker color sodas, they will have phosphoric acid in them. It gives it kind of that tart taste. One of the strongest acids that you may hopefully never come in contact with is sulfuric acid. That is in a car battery. It is also one of the most important industrial acids. They use it in cleaning or etching certain metals and those kinds of things, so it has some industrial use. Then the last one, the HC2H3O2, that is known as vinegar to us. That is actually acetic acid, or a dilute form of acetic acid. Now, bases, on the other hand, have almost always to do with some kind of cleaning agent. Sodium hydroxide, NaOH, is again kind of an industrial strength cleaner. So you see that used very often. We have used this in labs. The ammonium hydroxide is a cleaning agent, disinfectant. It is in things like ammonia. Obviously, it's kind of a relative of that. You would recognize the smell of this. It is a cleaner. And then the last one, for some dumb reason, I didn't put what magnesium hydroxide is. That is used in things like Tums or Rolaids. It is an antacid. Oops, sorry, that was written super messy. An antacid, you know, if you ever have heartburn, you can take this antacid and it will neutralize the acid in your stomach and help your stomach feel better. Okay, so now naming these guys. Acids, we haven't really talked about naming yet. When we get to bases, it'll be a review, but it's pretty straightforward. So when you are naming acids, there are two groups of acids, first of all. Binary, remember that word binary means two. So I'm dealing with two elements. One of them will be H, and then you will have one other element. And the form for this is hydro, and then you have the base of the element. I'm going to write the word base in that blank. And then you put an ic ending on it, and acid at the end. So HCl, which we have already mentioned, I've got one H and one Cl, so there are my two elements, is hydrochloric acid. So the chlor is the base. Now the next one, H2S, I still have two elements, a hydrogen and a sulfur. So when I name this one, it will be and this one is one of those that breaks the rules, hydrosulfuric acid. So it wouldn't be just hydrosulfic acid, it would be hydrosulfuric acid. HF is hydrofluor, so there's the base, ic acid. And then HI, hydroiodic acid. So pretty straightforward on those. Some of the other ones you'd have like hydrobromic acid. I can't think what other ones would be super common. But so there are not a lot of these. But again, follow that same format. Put a hydro at the beginning for the hydrogen, the base, and then ic acid. So that's binary acids. Okay, so now the ternary acids. These are hydrogen, of course, because that is one of the markers of an acid, along with a polyatomic. So now this is also pretty straightforward. It's kind of nice. There's no hydro, first of all, in these names. They just assume that an H is there because it's an acid. The only real change that you have is to change the ATE ending on the polyatomic to ic. So it's going to make something ic and then end with acid. So that first example, NO3 minus 1, so there's nitrate. When it is in an acid form, it has a hydrogen with it. It's 1H because the 1H cancels with the -1 of the NO3, and so you have a +1 -1. And then you just write the name nitric acid. So then the next one, ClO3 minus 1. It's -1 again, so I just need 1H. So I have HClO3, and that becomes chloric acid. All right, the next one, CO3, it's a -2 now. So because it's a -2, I need 2 H's. So H2CO3. CO3 on its own is carbonate. So when I put it in its acid form, it is carbonic acid. And then SO4, I get another -2. We've already seen this one in the notes. So H2SO4 is sulfuric acid. And that one again is a little bit tricky because it goes from sulfate to sulfuric acid. It wouldn't be, and again, if you put it, I wouldn't really count off, you're following the rules. If you put sulfic acid, you would probably hear that that sounds wrong. And so you would just kind of know that's one of those rule breakers. All right, PO4 -3. So we have 3 H's, so H3PO4. This is the one that's in like Cokes and stuff. That is, again, kind of goes back to the original phosphoric acid. That's an O. And then the last one, acetate, is a -1. And this one was also mentioned earlier. So you have HC2H3O2. Acetate becomes acetic acid, and that is the scientific name for vinegar. Okay. Now, naming bases, easy peasy, because this is basically how you've already been practicing naming anyway. So when you name a base, you have the metal name plus hydroxide. So this first set, these are going to be metals where we know the oxidation number. So basically metals from column 1 or column 2, or one of our special 3 in that little diagonal on your periodic table, aluminum, zinc, and silver. So when you name those, you just name the 2 parts. So for example, NaOH. Na is sodium, OH is hydroxide. And there you go, sodium hydroxide. The next one, MgOH2. The 2 doesn't do anything for us. Remember, just kind of ignore that and just name the elements. Mg is magnesium, so I would have magnesium hydroxide. And same for the next one. LiOH would be lithium hydroxide. And last but not least, AlOH3, aluminum hydroxide. So again, pretty much just a review of naming. Okay, so now the other 2 types of bases that you could have are bases that have transition metals or ammonium, which we'll get to. But transition metal, remember that's the middle section on your periodic table. These will have to have a Roman numeral in the name. You put it in parentheses right in the middle, and that Roman numeral tells you the charge on the metal. And this is really easy because you really don't have to figure it out. The Roman numeral will always be the number after the OH. So You don't have to do any math, you just have to put that in Roman numeral form. And so CuOH2 is copper, and then Roman numeral 2 hydroxide. I know that it's a 2, and if you needed to figure it out, if you forgot how to write it, OH is -1, and I have 2 of them, which means copper has to be +2. So that's where that that's where that Roman numeral 2 comes from. Okay, and then FeOH3. Fe is iron. I need to have a +3 charge to cancel out. So iron 3 hydroxide. Okay, and then the last one, the only base that contains ammonia, or the only base with a polyatomic at the beginning is ammonium, because ammonium is our only positive polyatomic. So that one is just ammonium hydroxide. Okay, so now real quick, a couple of theories on the acids and bases. We did this when you guys were freshmen, so it should be a little bit familiar maybe to you, but basically you have 2 different definitions. They kind of match up. One is very specific to water solutions and the other is very general, but they both basically say the same thing. So first of all, the Arrhenius acid. That is any substance that gives up a hydrogen in an aqueous solution. So the very first thing that I said about an acid was that. That is the chemical definition. It gives up hydrogen ions. A base, on the other hand, an Arrhenius base, is any substance that gives up an OH, that gives up a hydroxide in an aqueous solution. So here's where Arrhenius is a little bit limited. He's limited because he says it has to be in an aqueous solution. So he's saying it has to deal with water. And 99% of the time they do. So Arrhenius was pretty right. But a little less specific definition of acids and bases is the Bronsted-Lowry definitions. And these, instead of dealing strictly with water, although again, that's not wrong, they said it's not just about the H or the OH, it's about where it is going. And specifically, they looked at the hydrogens. And so Bronsted and Lowry, 2 different guys who worked on this, they said that an acid is any substance that donates a hydrogen. So if it gives up a hydrogen, very much like Arrhenius said, then it is an acid. Then they said for the base, they dropped the OH part and said, let's just look at what the hydrogen is doing. Let's just stick with one ion. And in a Bronsted-Lowry base, it is the substance that accepts the hydrogen. So in these equations, the reactions that I have down here at the bottom, the highlights, the red is an acid, the blue is a base. And these 2 meet both of those definitions. So the hydrogen that is given up is going to come from this HCl in the first equation, and it is going to donate a hydrogen to that water. When the water gains an extra hydrogen, that's where you see it become this H3O+. And then you have this negative chlorine ion that is kind of left over. But this compound right here, that is a hydronium ion, and it is what is basically measured as that positive charge. It's where the hydrogen went. Now in the other one, the NH3 is the base, and it is actually going to accept a hydrogen from that water. The water will donate a hydrogen, and you will end up with NH4+, which should be familiar to you. That's ammonium. And then you see down here at the end, the OH that's kind of left behind. And so you can kind of see where Arrhenius and also Bronsted-Lowry kind of got their information based on what was happening and how they're both right. Bronsted-Lowry, I think, is a little bit easier because you're just kind of following the H. You're seeing what the H is doing. Okay, last thing for today, conjugate acid-base pairs. This is just kind of a technique for identifying an acid and a base, but then also what they become, because essentially they become the opposite of themselves. They become something that has an H that it could donate, or they then gain the ability to accept an H. And so with these conjugates, you basically are looking at where the hydrogen is going. That is the thing that relates them, who lost a hydrogen and who gained the hydrogen. And so when you have a reaction, and we'll go through each one of these, you are going to have two pairs in each reaction. An acid with its conjugate base, and then a base with its conjugate acid. And so all you really need to do is look and see, where did the H go? Who lost the H and who gained the H? And so all four things in the reaction will get labeled. These are the exact same reactions that we had on the page before. They are, in this case, equilibrium reactions. Notice that you have a double-headed arrow in each of these. And that means that that H is basically just changing back and forth continuously from one compound to another. And so this is a continuous reaction. Okay, so first of all, we're going to label our HCl. So there is our acid. I'm just going to put an A for acid. And then notice what happens to that H. It is donated. It is gone now, essentially. And so what that substance becomes is going to be labeled as the conjugate base. I'm going to put a CB above that. And then the other substance, if I have an acid, that means I have to have something that has accepted my base, or my hydrogen, and then what it becomes. And it becomes this thing over here, and that becomes the conjugate acid. And I had a line here and it disappeared. I don't know why. Okay, so those are the pairs. You have an acid with its conjugate base and a base with its conjugate acid, and they essentially could go back. The acid on this side, this conjugate acid, could donate the hydrogen back to the conjugate base, and we would be back where we started. So that's why you see these as equilibrium reactions, because that's what is actually happening. Now in the next one, same thing, but now we're going to start with our base. So the NH3 is our base, and it will accept an acid, or I keep saying that, it will accept a hydrogen from water, and it will become a conjugate acid. It has a spare hydrogen that it could donate. And then our water is acting as that acid, is acting as the donator, and it will end up becoming a conjugate base because it could accept a hydrogen. And so pairwise, the base becomes the conjugate acid, the acid becomes the conjugate base, and they could switch back and forth. So your main thing on this is really just tracking where the H goes. Who gets the H and who gives up the H. The one that gives up is the acid. So the donator is the acid and the acceptor is the base. All right, that is it for today, guys. Hope your day is going well. Let me know if you have questions.